Okay, so once again, we've got a different variation of a Limacon. I don't know why there isn't an R here. There should be. Right away, before we even start this graphing process, we should be able to identify what this shape is going to look like in terms of one of these four variations. It comes from the values of the coefficient for cosine and then the constant after it. So this is what we're calling A. This is what we're calling B, right? And if we want to identify what this is supposed to look like, we want to look at the ratio of A to B, which in this case is 2/1, which is equal to 2. So we've got the ratio of A to B is equal to 2. This relationship, okay, if you'll reference your notes, it is going to tell us that we are looking at what we call a flat Limacon. Take a look at your notes. It's in it, okay? So I'm going to erase this real quick before we get going. So we know that it's going to look somewhat like a deflated ball laying on the ground, only it's not actually laying on the ground, is it? The second thing we want to look at is that this is a cosine-based Limacon, which means its symmetry is going to be over this axis, all right? Which is going to help us in graphing this because I don't have to graph every single point. If I know that whatever graph I get, and I'm just going to draw a rough sketch right now, whatever I get for this, okay, this top half, let's say this is the top half of this specific Limacon, that's all I have to graph. Because once I get those values are going to be mirrored down here on this part of the graph. Okay. Now, if you choose to, you can graph every single angle. That's fine by me. Okay. But if you're looking to conserve time, if you're looking at this and you want to take a creative approach to it, you don't have to graph every single point. All right. So what we start to come up with here is our range of values for theta and r. Remember, theta is our independent variable. This is where the freedom exists for us to put in whatever we want. All right, we're obviously going to go with 0 as being our first value. I'm going to let you plug these in on your own. I'm going to try and do them in my head as best I can. The cosine of a 0 degree or 0 radian angle is 1, and 1 plus 2 is 3. If we move over to pi over 6, the cosine of pi over 6 is 3 radical 2, or 3 radical 3 over 2, which is approximately, I believe, 0.8, and then I add 2 to that, so I'm going to call that 2.8. At pi over 4, we're dealing with 0.7-ish. 0.7 plus 2 is 2.7, give or take. These numbers might be wrong. You guys can call me out if you want. Pi over 3, the cosine of pi over 3 is 1/2. 1/2 plus 2 is 2.5. The cosine at pi over 2 is 0. At 0 to 2, we get 2. Jump on over to the other side here. This is where things start to get a little weird. At 2 pi over 3. Now, we skipped this one in class. We skipped this angle in class because we were dealing with sine here instead of cosine. Now what? Now we're dealing with cosine. The cosine of 2 pi over 3 and the cosine of pi over 3 are going to be different. Because once we get into these angles, all of these angles on the unit circle have negative x coordinates, which is what we're taking when we do cosine. So if I have 2 pi over 3, the cosine of 2 pi over 3 is negative 1/2, and this, when I add that to 2, is 1.5. Okay, I'm going to extend the page here a little bit. So we have the cosine of 3 pi over 4, that's going to be negative approximately 0.7. So if I add that to 2, now I'm at 1.3. Go over to 5 pi over 6. 5 pi over 6, the cosine of that is negative radical 3 over 2, which is in the neighborhood of negative 0.8. Add that to 1, you get 1.2. And then go all the way over to pi. The cosine of pi is negative 1. Add 2 to that, now you're at positive 1. So what we have are the points that we can use to plot here for the top half of this Limacon. So I'm going to go at 0 radians. I'm right here. If I'm going to go 0 radians, I'm going to move out a radius of 3. That's why we use r in case you were wondering. At pi over 6, it's 2.8. We'll put that there. At pi over 4, it's 2.7. At pi over 3, it's 2.5. pi over 2, it is 2. At 2 pi over 3, now this is where our numbers start to get less and less. At 3 pi over 4, we're at 1.3, which we'll put about right here. At 5 pi over 6, we were at, what was that, 1.2. And what you start to notice is how quickly, and then we're at 1 here, how quickly this shape begins to flatten out. Like we said, this is a flat limacon based on these coefficient values. Now, if you try to connect these points with a steady curve, what happens? These points that were here, okay, forgive the bowing out of the shape just a little bit, they were not moving much on the extremes of this. So when we get to this point, now we realize, okay, all of these points, all of the coordinates here, all of these values of r extended beyond this. These are going to be repeated down here. So these points are going to be mirror images down below. So I'm going to have a point here, I'm going to have a point here, I'm going to have a point here, and you see where we're headed after this point. Okay, we've got, again, this point at pi over 2, when it's 3 pi over 2, is going to be here. And we begin to bring the, oops, sorry, that's bad. No, that's not that bad. We're bringing it back to round off our shape. Okay, it is a bit of a fudging here at the end to make it look like it's a reflection, but you get the idea. This point, maybe I should retrace. Let me retrace this for a second. Okay, this point right here is going to be in the exact same spot at this pi over 6 angle. This is a pi over 6 angle. This is a pi over 6 angle. This point is directly below it. This point right here was at what? About 2.8 or so, somewhere in that neighborhood. It's going to be in the same spot over here. So we get an idea of what this shape was looking like from the beginning. Okay, forgive my drawing. I never said I was a good artist. But you're getting the idea of how we can recreate this shape on the bottom half of this polar grid and using the symmetry